you absent. I don't know why.
Actually, they were all complete, but there's some work emergency that happened
Or some of them.
to one of them actually, and then he had to leave. I just asked him to join back whenever he can.
Okay. So, Dr. Amtar, did you take the
That was
attendance?
basically that was for Naif Al Anazi.
Yeah, okay. Mr.
Otherwise,
Naif, huh? Yeah.
yeah, I would assume that everyone is here. Otherwise, we have 20
خلاص, okay.
now, and only Naif is missing.
Okay, Dr. Amtar.
Yeah.
I will, inshallah, you are seeing my screen, right?
Yes, I can see it.
Right. I'll just start the second part of our session.
Okay.
Here's some tips about solar resource or the location of you want to build a power plant, screening of the location. So you need to start with the location that have high normal solar irradiation. It's recommended to be about 6.7 or around 6 kilowatt per hour per meter square per day. You remember this unit, when you have kilowatt hour, it should be per meter square per day or per year, or it's not, because at the end for the design, we need kilowatt per meter square. Why we need the high solar irradiation? Because this will reduce the area needed to produce the power we want. Because if you have low solar irradiation, you will need large area, because you multiply the incident solar radiation by the area of the collector multiplied by the efficiency. Now, if you have low solar radiation, you need a large surface area of the collector, and this means more cost. So also we need to look at places that will not affect the site. I mean, where you build it, if it is sensitive from cultural, or if you have lake or river or something. So like in Egypt, we cannot go and build in a tourist place, or I mean old ancient temples, because we have the cultural wise we cannot. Also, we need land, flat land as much as possible. If we have more slope, like 1% to 3% land slope, we need to avoid that, especially for parabolic trough and linear fernal, because we need flat lands. Also, we need large area. If you have a space limited to 1 kilometer square, it might not be suitable, because you need large area in general. Also, you need your site to be as close as possible to the transmission lines of electricity. If you want to transmit the energy you produce to the utility or to network, you need to have it close to it. General briefing, good DNI range is up to 6 kilowatt per square meter per day. Capital cost will be between 4 and 8 million per megawatt. You remember in the gas turbine and steam turbine, we said the range is around $1,000 per kilowatt, or 1 million per megawatt. You see here, it can reach up to 8 million per megawatt. We'll see the Spain one first plant was about 10 million per megawatt. This is a huge difference because of the solar field. As I remind you, the conventional power plant, the capital cost is about $1,000 per kilowatt, or $1 million per megawatt. Here, it can reach up to $10 million per megawatt. This is 10 times almost the cost. Land requirements depend on the incident solar radiation. Remember, in the range of 6 kilowatt per meter square per day, then you can estimate how much, depend on the technology use, efficiency, you can need 6 to 10 acres per megawatt. Also, generation potential is 25 to 35 megawatt per square meter. generation is 1.8 million units per year. Depend if you have thermal storage or not. The capacity factor is 20 to 25%, can be increased to 30% if we use thermal storage. Again, I don't like this heat storage, but this is a good source that from which I got these slides. Anyway, now can you tell me what is why 20% capacity factor? Anyone can tell us what does that mean? Why low capacity factor here?
It's less than half the day. It's working.
Yeah, it's so because if we don't have solar, the capacity factor actually give us how many hours per year the power plant work and its full load, for example. So even during the day, it cannot work on full load if it is totally solar, but if it has storage, it can increase. But also during winter season, night time, it's not working, right? So that's why it's low capacity factor. If we have cogeneration, the operation cost or levelized energy cost can go between $0.1 to $0.2 per kilowatt hour. Lifetime is around 40 years, usually 20 to 25 years. Payback period from 5 to 12 years. Installation period from 2 to 3 years, but depend on the size. Again, the working cycle can be Rankine, and this what is drawn here is Rankine cycle, or Brighton or Stirling. Stirling, as I said, it is very suitable to solar dish, but a Brighton cycle usually with the solar tower, Rankine cycle with the parabolic trough and linear Fresnel. This is a map in 2008 when we started actually looking for working on the solar. We made the literature, and this plant gave us the with this solar map potential, it gives the installed capacity and the planned or in pipeline, like in Europe, there was the 12 megawatt installed at 2008, but after that 2009, 2010, they built more. Asia, as you see here, they don't have, but now India is building. Iran also has some plant, I think Azad power plant in Iran. Middle East, we have planned, we have in Morocco, Algeria, Libya, we have in Egypt also one. In US, they have at that time the highest installed solar, concentrated solar power. This more 1 year later, they installed, and also what is in the planning, the operation at that time was about 1.2 gigawatt. You see here, Spain alone have 730 megawatt. US is more. Iran also appeared in the picture. India is under construction, but remember this is in 2009, 2010. So here, this also our literature. At that time, we were making our own literature survey, try to identifying where are the solar CSP power plant built and what are the technology. You can see most of it parabolic trough, but solar tower is there, linear Fresnel appeared. Also, this some quick comparison of plant in US, but yeah. By the way, I put the links. You can just visit these links and get updated data. This comparison between the temperature level and working fluid and also the technology used. This project in having steam as the working fluid, the temperature go to 649, and technology with Rankine cycle. I think this is parabolic trough. We have working fluid oil or sodium. Sodium is actually can also melt at low temperature reach, but sodium is the solar field. Actually, I have some table for different fluids or heat transfer fluid that go into the solar field. Here, the technology here, parabolic trough, two-axis parabolic trough, central receiver with sodium, a central receiver with water and steam that we can generate steam directly. And thermal storage here is giving the volume in meter cube, but in the first one, none, no thermal storage. Second, we have thermal storage in oil, and 114 cubic meter of oil. We have liquid sodium, we store like the molten salt, but we have here also, we can store thermal energy in rock, oil, and sand. So we have a bulk body of, we can have a pipe of this working fluid that go to the solar field. This pipe go inside or surrounded in a big tank that include rocks, oil, and sand around it. Then the heat will be transferred to this bulk body and keep it due to its thermal capacity for longer time. Of course, the overall tank is insulated and the plant capacity is 10 megawatt. This Andalusia Solar One first plant in Spain, in Andalusia. They build it on stages 1, 2, and 3. They keep adding to the plant. This longitude and latitude, the first one capacity was 50 megawatt, and it started, I think, in 2009. As I said, the name is Andalusia Solar 1, 2, and 3, just the phases. Annual DNI at that location is about 2,000. You see annual here, not per day. It's about 2,000 kilowatt hour per square meter per annum or per year. Technology used is a parabolic trough, and this is the company name. Land utilized is about 195 hectares or 9.6 acres per megawatt. 9.6 acres per megawatt. Construction period, 2 years, almost July to 2006 to October 2008. Estimated lifetime 40 years. Entire plant efficiency is 28% during the peak, but average annual is 15%. Capacity factor 20%. Energy generated is 180 gigawatt hour per year. Heat storage is used, and wet cooling system. The developer company is these two companies. This is the principle of Andalusia Solar One. It is totally solar. It's no, as I said before, we can integrate here conventional boiler to work at night. This might reduce the size of the thermal storage here, or even eliminate it if at night you work with the conventional power plant. This is actually depend on the need of electricity and environmental issues. You can, so here some other major component specification. The solar field, as I said, it is a parabolic trough as shown here in this picture. I want to remind you with the parabolic trough, when you have a tracking axis, you need to move all the structure to keep following the sun. And that's why you have these flexible joining pipes to connect to, you see it is very long here and different rows, as we'll see in a coming picture. The area of this parabolic trough is about 5 million meter square, mirrors about 200,000 mirrors. The length of this pipe is about 90 kilometers, maybe not a straight line, but you have, let us say here, 1 kilometer, then second, maybe you have 90 rows here connected in series or parallel, I think in parallel, in series. Field efficiency, solar field efficiency is 70% at the peak, but 50% on average per year. Sustained wind speed is about 13.6 meters per second. This is high speed, so the structure here should take into consideration this wind effect from a stress point of view. Thermal storage is used. We use this type of molten salt, nitrate, which is 60% sodium. Then two tank, and I recall one at 290 degree, one at 386 degree. Storage capacity is 28,000 ton of this molten salt. This storage or thermal storage can keep the plant working for 7.5 hours extra than the solar time. Of course, we need cooling water for the power plant, for the condenser. As I said here, we have this cooling system. We need this because there is evaporation in this cooling tower to cool the condenser. You have to make up, because you depend on evaporation here to evaporative cooling, so evaporate some water. So the water you need for cooling is about 870,000 cubic meter per year, or 1.2 gallon of water per kilowatt hour. Now I have a question. Why solar power plant, if you have a steam cycle, you need cooling tower? Why not to use to build a plant near the sea and use the seawater for cooling? Why most of the solar, we have this cooling tower required? Anybody can tell from the previous lecture?
I think for discharging the water to the sea or the river, it has to be in the same temperature as the water in the sea. So because it will be a little bit warmer than the sea temperature.
Yeah, but the temperature, always the seawater will be less than that of the air. The seawater temperature will be less than that of the air. But of course, if you have evaporative cooling, it will be less than the normal water. But the cost to build the cooling tower actually might not justify, if you are near the sea, it will not justify to build a cooling tower near the sea. You just take the water from the sea, cool the condenser, and put it back. We have all power plant here, like in Azizia power plant, to Pale, Ghazlan power plant, to Graya power plant, all here on the Gulf. You just take the seawater and return it back. No cooling tower there.
But how about if the stream is not that big, like rivers?
But actually, I asked it to link to the first lecture. Remember the diffuse radiation and normal direct radiation? The diffuse, actually, because near the sea, we have a lot of humidity in the air, and most of the sun radiation will be diffused. It will be not normal to the surface. So because of the diffuse solar radiation is high there near the sea, you need to build the especially CSP away from the sea. So in this case, if you want to use the seawater, you might need a big pipeline to connect. So that's why you need to have it on dry and clear sky place, not near the sea. That's why you might need cooling tower.
Excuse me, what?
It's clear?
Again.
As we said, when we have the solar radiation coming from the sun straight to the earth, if you have your air near the place on the site of the plant, you have a lot of humidity. This water vapor molecule or the water molecule will scatter the light, and it will change its angle, right? That's what we call diffuse. I talk about in the first or second slide of the first lecture. So near the sea, it is not good to build CSP near the sea. Clear?
Yes.
Right. So quickly here, capital cost is 380 million in the Andalusia Solar 1. If you calculate here 380 million and you have 50 megawatt, if you divide it will be about $7.5 million per kilowatt. But we'll see when we have the extension, the cost went higher because the extension was in a later time. Also financially, equity was 20% and debit 80%. Carbon emission reduction is 150,000 ton per year. This is the contract, and this tariff was about 0.27 euro per kilowatt hour, or this is levelized energy cost. You remember the levelized energy cost we have studied in our module 5 and 6. Kilowatt hour cost is $0.38 or 0.27 euro. Building was started in September 2008, and it can go for 25 years. Electricity for people of around country of about 200,000 people. It gave operation and maintenance job for about 40%. This is a breakdown for the extension of Andalusia 1 and 2, which was produced 103 megawatt parabolic trough with the 6.3 storage, thermal storage of thermal storage. This is correct. With wet cooling, I mean this evaporative cooling technology. If you can see the breakdown of the cost, you have site improvement or preparation 3% of the cost. Solar field is 45%. This is the major cost. Heat transfer fluid system, the fluid itself and the pumping system is 10%. Thermal energy storage is still huge, 20%. Power block, the power block, which is the turbine and the electric generator, and this cost is 12%. Energy phase change material is 3%, contingency 7%. Total estimate cost is $1 billion, about $1 billion for 100 megawatts. So if you see the cost per kilowatt is about 10 million per megawatt, or here it is 9,000 per kilowatt, or 10,000 per kilowatt, or 10 million per megawatt. So cost is about 9 to 10 times of conventional system. It's very high cost to build a standalone solar system. And here the thermal energy storage you can see is 20% cost for 6 hours after the sunset. If you need it more, like for 10 hours, if it is linear relation, so if I need 12 hours, so this cost will be 24%, it will double. But the thermal storage is very bulky, need more space, and it need really space. Also some challenges for this thermal storage. We said that we can change the material to molten salt. It might be less size. Also, you can use one tank, to use this stratified phenomena that cold fluid go down and hot fluid go up, or have two sections in the same tank, and instead of having two storage tank, we can use phase change material. We can use a steam accumulator. We can use concrete material. I mean, it has more thermal capacity or mass time. Specific heat might be higher than that of the fluid used. Also, we can use improve the receiver itself, the vacuum tube. Actually, there is development of having more vacuum, or to guarantee there is vacuum also coating. Also, there are some people working now to have in the fluid or inside the receiver, the heat transfer fluid in the receiver, they put nanomaterial or phase change material to absorb more energy from the solar incident solar radiation, because you have a fluid flowing here. So it depends on the speed of the fluid, depend on the mass flow rate, depend on the heat transfer rate. but also depend on the thermal capacity of that fluid. But if you added the nanomaterial, like carbon tubes, nanotube, carbon nanotube, it can increase the thermal capacity, but you can increase this more by putting phase exchange material. But putting phase exchange material that you needed to go with the flow, you need to produce nano capsules, and this inside nano capsules, nano because you want to have it entrained with the fluid, go with the fluid easily while pumping and this and that. And inside you put the phase exchange material that when it melts, it absorbs a lot of heat, then it will freeze again when you cool it, then absorb again when it comes. So this will raise the thermal capacity of the absorber. You can absorb more heat from the same receiver. Also, working fluid, we can use synthesized aromatic fluids, like it can go up to 400 degrees, but we can use molten salt that can go up to 550 degrees. Actually, 400 degrees and 550 degrees for the heat source in the power plant make this limited to a steam cycle or even organic Rankine cycle. Talking about gas turbine, then you need a very high temperature. We said we have to go inlet to the gas turbine, it should be 800, 1000 degrees or 1200 degrees. Just to give you idea about the water consumption, because we use evaporative cooling, water consumption is a concern, and you can see the ranges here of the water consumption, like 800 gallons per megawatt hour. If you have dry cooling, you might need only 780 gallon per megawatt hour different. If you have combination between hybrid or hybrid between wet mean, we use the cooling tower like this one. But here we have air cooled. Air cooled that you have a condenser like that one in your like the radiator, your car radiator, or the condenser of air conditioning system, that you have a fin and a tube heat exchanger, but it will need large area, and actually material-wise it will be costly, but also it might not be efficient in condensation. But if you use cooling tower or wet cooling and dry cooling, you might reduce the water consumption and at the same time use the benefit of both. Also, we have problem of low capacity factor, high capital cost. These are another examples. Another plant in Spain that is based on solar tower. You can see this is a parabolic trough one, and this is a solar tower just near it. This is picture of a plant in US and California, built in 1984 to between 84 and 91. It's a parabolic trough. Just for your information, the first power plant using CSP in the world was built in Egypt on about 1890 or something, maybe 120 years back or 140 years back. It was in Maadi in Egypt. I mean, British company built it actually for water irrigation, 2 power pumps for water irrigation. But you see the parabolic trough here, rows is very long, and then this pipe will go in series to be connected here, and this will be connected here, and so on. It go here and connect it back here, then come here, connect. So these rows actually are connected in series, as you can see here. This is clear. This pipe go up to the end, then connected from the back here, come here all the way, then this hot water go to the third row, all the way to the back and connected from the back to come here. So if we, like a string, like a YouTube or so. So this big field is actually one pipe. That's why we said 90 kilometer. But this is, the power plant is big, 354 megawatt. But actually, if you look at the steam generated from this power or this solar field, I'll just to tell you, one steam turbine in Ghazlan power plant is 600 megawatt. And the Ghazlan power plant has about eight steam turbines, produce about 4,000 megawatt. So here, all this solar field produce can feed only, half turbine or turbine of half capacity of one of that of Ghazlan power plant. Just to imagine what is the size required. I think this is in Nevada, USA. Actually, once I was in 2017, I think I was traveling from Nevada to Texas, and I saw this from the aeroplane. I was seeing it, some shiny surface. I say, are these lakes? But it is solar field actually. Either it is PV or here this parabolic trough. I was thinking they have many of these on Nevada desert. This is again in Andalusia, Spain, the one we studied. This is a parabolic dish. You can see it is 25 kilowatt in Mexico City. It's not for large scale application like in megawatt. This is not megawatt scale. This is a 5 megawatt in California, demonstration of 5 megawatt. This is a linear Fresnel collectors. This is solar tower one in for 5 megawatt by eSolar in California. And I think here for actually, you can see here, this is the receiver where this heliostat mirrors reflect the solar radiation to the receiver here, where you heat actually the air for a gas turbine. And the GE, I remember while we are working with MIT, GE had a contract with MIT to develop a gas turbine, the solar gas turbines that can be installed here in this tower, in this receiver itself, to take this hot air and rotate the turbine and the generator, and then you can have the electricity coming from a cable inside the tower to the network. You can see here these transmission lines. We have one here in Naqab Desert near Jordan, 6 megawatt. I end this part and I want to start, if you don't mind, we can start immediately the third part. Then we have some time to talk about the projects. Yes.
I have a question just for
Please.
my understanding now. Now, as you mentioned now, Ghazlan, it's around, the total capacity is around 4,000 megawatt, okay?
Yes.
While all the renewable energy that you introduced it now is only small size. We are talking about 50, we are talking about 100, something like this. So
yes,
how we can generate this amount of power from renewable energy, okay, while we have this amount from the oil or the gas, okay, the utility from oil, gas. We're talking here about only Ghazlan producing this much of megawatt. So I cannot imagine.
Yeah, Ghazlan is about 4,000 megawatt. Goraya also about 4,000 megawatt. Another plant that is private near Goraya is about 4,000 megawatt. Ghazlan, Goraya, sorry, and the plant near it, the thick one and this private one are combined cycle technology. That gas turbine operate steam turbine.
Yes.
Actually, this is a totally economic issue and environmental issue as well. You remember when we were talking about environmental impact, we said that some countries are now applying carbon taxes. And you remember I gave this example that you have it in the homework and in the exam to build this carbon capture facility and pipeline for sequestration is more feasible, or to pay the carbon tax and just use the conventional plant without carbon capture. Is this, which one is more economic to you? But also, as we said, this is one option at that time to make carbon capture, but the other option is to reduce burning the fuel by using a renewable energy, right? Because if you use solar, so you reduce the amount of fuel you burn, so you reduce the carbon dioxide emission. So if there is a carbon taxes will come, you will compare to build a solar plant beside your main plant, or you depend totally on solar and save the carbon taxes to you because the government give you incentive. Or if now in US, they force each power plant, because the electricity production in US is private, it's totally private. So they force each power plant to produce 20% of the electricity from renewable sources. So now each plant owner think about what is the suitable technology. I have a conventional power plant that is already there. So what renewable energy technology I can use? Can I use agricultural waste if I am near a farm? So I take this straw and burn it instead of burning coal. Or I can take this agricultural waste, I make gasification, I convert it to gaseous fuel, so I burn it instead of natural gas. This is also renewable, right? Or I build solar power, or I build wind energy to integrate it with my plant to satisfy this 20% of my production from renewable. Okay, so it depends on the laws, depend on the cost at the end of the electricity you are producing, depend on what stringent regulation in the country you are in to produce your electricity.
Yes, you're
right,
right, Doctor. But what I
But
mean here,
nowadays, let me continue. When the price of oil reaches $140 per barrel, all the world tried to develop more the solar technology, and the result is PV now is very cheap, right? So nowadays also you are thinking about electricity production as centralized, like in this big power plant, Ghazlan and Guraya and this, or you make each house produce its electricity using PV.
yes, you're right.
This is also strategic thinking, right?
Yeah.
So now, world now is moving in transition situation between going fully to renewable, where it's very costly at the moment, but with the development of the technology and making the technology available and going to mass production, then the prices go low, right?
Yes, you're right.
Like PV now is very cheap. Wind energy is very cheap because the technology developed, but maybe 20, 30 years back, it was so expensive, and also its efficiency was low. Now you find most of the building now, new building having the roof or even in the walls. In Europe now, there is technology to have PV with color. So you can have it on the walls of the building with the different attractive colors, not only on the roofs. So integrating PV with building now is the, is the art now. People in architecture are working on that. So now, as you said, this is a concern. How to produce this? If we have a standalone solar, we need thermal storage, and this is add to the cost. By the way, I put one of the papers we worked on. It's published in Solar Base Conference held in Korea last year. Collaboration with the solar company in UK. We compared generating solar electricity using the CSP against that for PV. And we see which more economic, the central with thermal storage, CSP, or PV, central PV, and also large plant of PV to produce, I don't recall how much, 150 megawatt, but the paper is there. You can read and see what are the elements based on what you decide, right? At the end, it's an economic and environment decision. But at the end, it is economic, because if you have in your country carbon tax, then producing oil is cheap, but the carbon tax is high. Like nowadays, or a few months back, oil reached $20 per barrel. It was a few years back, 140. It's an economic issue, isn't it? I remember we have been visited by a team from Tokyo University. They were nice. They are professors and they are developing technology for PV, solar PV or photovoltaic technologies. They said we developed in the lab PV that produce electricity with efficiency 40% in the lab. But of course, we have here in Saudi Arabia, harsh environment, high temperature, and maybe dust as well, because we are a desert country. Then they said, we give you the technology of solar because you have the solar energy. We developed the know-how of the PV, but we don't have the solar. Now you have the solar, you might need the oil. You might not need the oil for energy, but since we don't have solar, we need your oil. So we give you the technology of PV and you give us the oil. He was putting it in a joke way, but he's right. Some places, you cannot use solar on it, you don't have it. But here we have it, but also at the same time, we have the oil. So actually with this scenario that we have solar and we have the oil, why not to marry them? This is what I did with MIT in 2010 up to 2016. We started the idea in 2008, 2009 to integrate solar to conventional power plant. And I will talk about this soon, inshallah, in this lecture. Okay. So integrate concentrated solar power to the utility. The cost of solar power compared to coal or natural gas or wind is higher. Also, for economic basis, you need to build large scale. Also, land use is very costly and it has impact. You need 5 to 10 acres per megawatt electric. So you need also the land to be clear. Water consumption is high, as I said, since you need to build it usually in desert or away from the sea. So you need to use cooling tower. In this case, you need 3 meter cube per megawatt hour. Air-cooled plants use 90% less water, but cost more and run at lower efficiency. Transmission is required since you are going to build it in a far land or area far from the cities. To have available cheap land, you need to build it far, but you need to transmit it or connect it to the network. So transmission will be costly. Let me go to the show mode. Actually, we have research to develop energy storage to make it, as I said, more compact, has more capacity by putting phase change material and other things. There is the thermal capacity of it. Why not to have direct steam generation? Direct steam regeneration, the problem in it, what we need in the power plant, in the steam power plant, we need steam at high pressure, high temperature. So if you have in this receiver of the parabolic trough, you have a working fluid at low pressure, it's okay because of leakage, especially in the flexible joints between the pipes. But now if you want to generate the steam directly in the receiver, then you need to have the high pressure, which the material of the receiver should be more costly. The flexible joint design and fabrication will be more costly. And also when the vapor is changed to, liquid water, this is phase change. This is actually give you a high heat transfer rate, but when it becomes vapor, the heat transfer rate become less. What is the benefit of direct steam generation? You don't have this resistance of having heat transfer fluid in between the solar field and your boiler, because this is when you put fluid in between this, you use non-contact heat transfer heat exchanger, which add thermal resistance. You put a barrier actually between the solar field and your working fluid, which is here the water in the boiler. When you use directly water come into the parabolic trough receiver, the heat transfer process will be more efficient. And of course, you will save the money for the heat exchanger, you save the money for the heat transfer fluid. But as I said, the pressure will be high. Also, there are some research in improving the reflector performance and durability. Also, resource, as we said, building or designing a power plant and building a power plant depend on the proper data record of the solar radiation. You should be fully having the accurate data for the solar radiation, even it is random. In nature, since you might have a cloudy day that is not happened before, or you have a dust storm, or this is unpredictable. But if you have kept a record for a long time, as what people are doing now in Kakera and Aramco, they keep recording data. Even I was in a meeting with Aramco, they are recording the passes of the sandstorm. You remember, we have some times of the year, we have sandstorm, and this sandstorm was recorded have some pass. It go for some pass from when it started coming from the north, from Iraq or something. So it goes through some passes. So Aramco now is drawing maps for these passes, sandstorm passes, to avoid building any solar PV or solar CSP in this place. Also, the control of the tracking of the parabolic trough or heliostat mirrors or Fresnel mirrors, you need to improve the control. People now in control area, they study how to control or to make your mirror track the sun perfectly during the day and during the year. They use genetic algorithms. They use this really intelligent or artificial intelligence to build a real control or efficient control system that increase the efficiency. Also, some are some advantage of integrating it is you can match the load profile if you have integration with the utility. Also, you can if you have a thermal storage, you can have this cloud issues or sandstorm that affect the mirrors. Energy storage can provide power after sunset or make it dispatchable. You can have continuous production. Also, this idea of hybridizing the solar or CSP with fossil power plant. Do you remember in this steam cycle when I plot or I said we can add parallel boiler, conventional natural gas boiler, but of course with some plumbing to have it only natural gas or fossil fuel or solar or both. We can take from both with these valves or flow controls between the pipes. This has a key idea actually. And as I said, we can integrate with the conventional Rankine cycle the way I draw it. We can integrate with conventional gas turbine, but with gas turbine, we need a solar tower because we need high temperature. We can integrate with the combined cycle. When we come to the combined cycle, we need to study. We have gas side, gas turbine side, and we have the steam cycle. We add the solar in the air side or the water side. If we add in the air side, we need to preheat the air before the combustion chamber, or we have what we call fuel reforming. Now let me tell you how we thought about our project that actually took 6 to 7 years. First, we looked at if we need to integrate solar to conventional power plant. All right? First of all, you need to build a solar field, right or wrong? Yes. And the solar field, actually, because we assume that we are going to integrate the solar field either with a new built power plant, because Saudi Arabia, for example, may be building, is maintaining what plant they have now, but they build a new plants. Either here, Guraya Power Plant 1, it was 2,000 megawatt. And over last 3-4 years, they built another phase, which is another 2,000 megawatt. So either the plant, existing plant, you build the new ones, or now for a new city, for example, everything is new. You are building new plants. So of course, you are going to generate electricity, right? So you generate electricity by conventional power plant plus solar, or solar alone with thermal storage, or hybrid. Now we talk about the hybrid. We said we have oil, that is cheap. We can use it during night. We have a lot of solar that we can use it during the day, right? But if we use solar during the day, then the capacity factor is low. Why not to try to use solar at night? So at night you can have thermal storage. What type of thermal storage? But first of all, let me put my way of thinking clear to you. Now we are going to build a solar field. That is very expensive, right? So if I have energy from this solar field, this means I have very expensive fuel, right or wrong?
Yes.
Now, if this very expensive fuel, I have it, should I burn it in a low efficiency power plant to convert it to electricity, or I should burn it in a very efficient power plant? If I have expensive fuel, I should burn it or use it in a very efficient power plant. Otherwise, I'm losing a lot of money, isn't it?
Yes.
So the idea came like this. What is the most efficient power plant of the conventional one we studied is the combined cycle. Right or wrong?
Yes. Right.
Yes.
Yes.
So we decided to make our study or to integrate solar with combined cycles. All right. Now in the combined cycle, we have the water side and we have the air side. In the gas turbine, the inlet to the gas turbine temperature, how much? About 1,000 degrees for the gas turbine. You remember module 4?
The temperature?
Yeah, the inlet to the gas turbine. Usually how much?
Under the ambient, 25 to 30.
No, the inlet to the turbine. I mean, you have the inlet to the compressor, then combustion chamber, then the turbine itself.
Yeah, it's very high. 1,000?
1,000 probably.
Right. And for a steam turbine, what is the maximum possible temperature? We said about 500 after the boiler. After the superheated steam should be around 500. Otherwise, we have material problems. Remember these issues, right?
Yes.
Yes.
So should we add to the water side, the heat, solar heat, we add it to the water side where we have temperature about 400 degree, 500 degree, or we add it in the gas turbine where the temperature is 1,000 degree?
Water side, we cannot add it to the gas.
Yeah, actually thermodynamic wise, when you add the heat at high temperature, you get higher efficiency. So adding the heat or the solar energy in the gas turbine side, you expect more efficiency. This energy you added at high temperature, you have a very high potential to take more work from it. But if you add it at low temperature, it is close to the dead state. So the potential or exergy it has is less than if you add it at high temperature. But what is the factor now that will help me decide I add it in the water side or add it in the gas side? The cost. Because if I want to add heat in the gas side, I need to build the solar tower field. If I want to add in the water side, I will build parabolic trough field. The capital cost of the building the solar field and the energy consumption I use and the cost I produce will decide which technology. So here we have in the air side actually either preheat the air before the combustion chamber actually, or the other option. We can heat the air before the combustion chamber or after. I mean, we parallel to the combustion chamber, because this is both I studied.
So Dr. Ismail, here you decided to add it with the to the gas turbine, to the gas cycle.
Actually, we decided to use a combined cycle.
Yes, but you will add the solar where in the.
Let me continue my story. This is actually, I want to remind you, with the steam cycle. This is a conventional steam cycle. You have the boiler, right? You burn a fuel in the boiler. So you generate steam, rotate the steam turbine and generator, condense it using cooling tower or whatever, then they pump to the feed water heater and complete the cycle. Here you have whatever ashes or whatever CO2 coming outside. And this is the solar, right? Now, when we combined solar with the complete steam cycle, only with the steam cycle, this is type of integration. I mean, we have this steam cycle, we add beside the boiler, either while we heat the feed water by solar. So before it go to boiler, we can heat it by solar collector to help the feed water. You remember when we have the regenerative cycle, we're taking some steam from bleeding steam from the turbine to heat the feed water, and this will reduce the power output of the turbine. You remember that? Regenerative cycle?
Yes, Doctor. Yeah.
Yes.
This Dr. Antar explained this. But now if instead of heating the feed water by bleeding steam from the turbine, we stop that and we heat by solar field. Of course, this will increase the power produced in the turbine, and we reduce the energy we pay for burning fuel. Also, if we help the boiler itself, we have the conventional boiler, and parallel to it, we have the solar field. During the day, we boil the steam using the solar collector. During night, we use the conventional boiler, right? This will reduce the fuel consumption. So here, even adding the solar here, we selected regenerative cycle. Why we selected regenerative cycle? Because it is the highest efficiency in steam cycle or Rankine cycle arrangement. The highest efficiency is the regenerative cycle. So we select a very efficient cycle first. Then this is the solar tower technology. As I said, we can have a total steam by solar tower. I mean here, when I said boiler, I can use parabolic trough in the solar field, or I can use solar tower instead of parabolic trough, isn't it? Now, this is the example in your book, the two problem I found in just a numeric number on evaluating, integrating solar tower to a steam cycle, but we'll solve it later because I need to finish. This is a gas turbine. The conventional one, we have the air coming to the compressor, or compressor sucks the air and compress it to high pressure. Then you add fuel here in the combustion chamber, then you have the expansion to the turbine. Actually, I can add solar tower to heat the air here. So if I heated the air before the combustion chamber, so for example, here after the compressor, if the air at 450 degrees, of course, no need to put parabolic trough because the parabolic trough maximum temperature is 400, 500. So the best here is to add solar tower. Then if you heat it to 800 or 600, the fuel you burn was to heat it to 1200. Now you heat it to 600 already, then you need to burn less fuel if you have hot air here. But to burn less fuel, you have hot air here coming, then you have what we call high temperature combustion, and this will, the combustion characteristic will vary. That's why we study combustion also. So we have phase of the project to study the combustion characteristic and the analysis. And we have a lot of work on combustion. I didn't put the papers here about combustion, but we have a lot of work on combustion here at high temperature, oxyco, and other issues. Now, if I have a solar tower that can heat the air up to 1200 degrees, so I can bypass the combustion chamber, stop burning fuel at all in the morning, and all the heat coming from solar, I take the air here to solar tower, heat it and bring it back to the combustion to the turbine. Or I can take part of the air, I heat it in the solar, part of the air I heat it in the combustion chamber and mix here. We have different scenarios actually. We studied different scenarios. It's an optimization problem. So either to just heat the air for a small tower here to up to 600 degrees, 700 degrees, then you reduce the fuel, then you produce here 1200, or you bypass completely with some valves, of course. At daytime, you don't use fuel at all. At nighttime, use fuel, or you split the air in between, depend on the amount of solar. If you have high solar, you take more air to the solar collector. If you have low solar in the sunrise or sunset or in the winter, you take more air to the combustion chamber. And of course, you burn more fuel. So this is an optimization. How to split, the splitting ratio is an optimization issue. And we have some work on that. Even some paper is under preparation now for this splitting ratio. But again here, you add the temperature or you add the solar energy at high temperature level, 12 degree, 1200 degree or 1000 degree. This is mean you have high potential to produce more work. And remember, if you added the this in a combined cycle, this is the solar, how we heat before the, if it is just a gas turbine, and this is the chimney, but you depend on how much heat you added here. If you heated, you could heat up to 1000, then almost you don't need to inject the fuel here, right? If you heated up to 600, then you need to continue to 1200 by adding more fuel here, and so on. Depend on the day, depend on the location, depend on the time of the day, and so on. But also, as I said, if you have optimization problem, we can divide the air part to go to here part, bypass the combustion chamber, and so on. This is different ways to where we add the solar to gas turbine cycle. This is a combined cycle. As I said, this is the gas turbine, and this is the heat recovery steam generator going to the steam turbine. So we help this here add more heat in the solar by the solar field in the water side, or try to heat here the air coming to the combustion chamber, or bypass the combustion chamber and reduce the fuel. This is our work. This is the first master student worked with me in the project. We have the gas turbine. We try to help the heat recovery steam generator to, this is a conventional combined cycle. This is a gas turbine, heat recovery steam generation. This is the steam cycle. And this is a boiler actually for the steam cycle that takes the exhaust to heat the water. Now we try to add solar here to help the feed water heating, or we add solar here to help the boiler. And we have also some option here to help the gas turbine before the combustion chamber. As I said, if we have high solar radiation during noon time of a summer day, June or something, we can heat the air up to temperature I want in the gas turbine, 1200 degrees, so I don't need to burn fuel. So actually in your program or in your model, you write if statement. You have the air coming from the compressor to this temperature T2 over T1 equal P2 over P1 to the power comma to the power minus 1, K minus 1 over K. Then go to here to solar heating, you get one here for 50 degree, and you get here to 800. Now, if the temperature, you can put if statement in your code. If the temperature is 1200, khalas, don't burn fuel, right? Make the fuel consumption 0. Or you put a sensor here in real life, you put a sensor to measure the temperature. If the temperature is 1000 or 1200, which you need it here at the inlet, you give a signal to the fuel valve, stop. So in the modeling, you can write if statement. In real life, you can put a sensor and the flow controller. If the temperature reaches to the want after the solar tower, stop the fuel. If the temperature is still lower than what you want at the inlet of the gas turbine, open the fuel and add more fuel to burn. So here you are adding the solar energy at where? At the source. Because after this gas turbine, whatever energy here in the exhaust, it will help the water side. So if you have solar with fuel or solar without fuel, heating the gas turbine to work, the exhaust also in the water side will be affected by whatever solar here. So that's why when you add the solar in the gas turbine side in a combined cycle, actually you are adding it to the two cycle, to the gas turbine, and the remaining from after the gas turbine go to the steam cycle. But if you add here in the steam cycle, you gas turbine is still having its power from the fuel conventional, but the steam cycle you help it. But you help it at low temperature, but you will not affect the gas turbine. Here, you affect the gas turbine and the water cycle. Actually, at the beginning, if you add the energy at high temperature, you have more potential because you added at 1000 degrees, then you have the expansion up to the atmospheric temperature, from 1000 to atmospheric temperature. But if you add it in at 400 in the water side, you have the expansion up to the atmospheric temperature, isn't it? So these delta T somehow represent the potential you have to do work. But if you have delta T from high temperature to atmospheric, from 1000 to atmospheric compared to 400 to atmospheric, then you better select the high range of temperature, isn't it? To give yourself more chance to produce energy. This is a schematic or cartoon to show if I have a solarized gas turbine integrated with a steam cycle through here the exhaust, this is sort of heat recovery steam generation, but cartoon wise. This is the metrics, how to evaluate the performance of solar power plant. You can look at it yourself if needed, another type of cogeneration cycle, this is actually, you need to pay attention here because one of the project is the district heating against solar heating, individual solar heating in houses. You compare district heating. This is, I think, first topic in the projects. So I think this problem is under, it should be taken into consideration. Actually, we studied a combined cycle where to add the heat in the water side or in the gas turbine side. But we selected with another one of my master students, Mr. Dabwan. He's now a professor or finished his PhD in China. We have another type of cogeneration. Cogeneration is a cycle that produce power and heat, for example, that you have a gas turbine and the exhaust is to generate steam for a chemical process. Actually, we take this example from Ras Tanura, a petrochemical industry, where they have a gas turbine, they produce steam for chemical process or petrochemical process using gas turbine and heat recovery steam generation to produce the steam. This is the information we have from Ras Tanura plant. This gas turbine produce 150 megawatt electricity, and the heat recovery steam generation by the exhaust producing a steam of 80.4 kilogram per second at pressure 45 bar and temperature 394 degree. So we wanted to take a typical power plant that is already up and running, and we study if we want to integrate solar energy to it. And also we try to study the different possibilities, like trying to help the heat recovery steam generator to produce the steam we want, because this is the real product we want. The factory need the steam. Electricity was a byproduct because you can take it from the utility, but the steam they have to generate it. So in this case, if we added solar tower to help the heat recovery steam generation, so we don't need to have more energy from the gas turbine. So we can use the smaller gas turbine to save the energy or the capital cost. And we depend more on the steam generation from the solar field with the help of the gas turbine. So we studied different gas turbine. Actually, we said that the exist power plant or system in Ras Tanura petrochemical compound, they have 150 megawatt electricity gas turbine. So we studied, it has its own capital cost with the exhaust here enough to generate this steam. So we decided to study different gas turbine size from 30 megawatt, 40, 50, 60, up to 150. 150, we don't need much solar here, or we don't need duct burner to help generate the steam we want. Because 150, the exhaust is large enough to generate the steam we want. So we don't have room for solar or for duct burner. But if we reduce to 30 megawatt, the exhaust gas is not enough to generate the steam. So we have to use a solar field in the morning, and duct burner, we burn fuel here in the heat recovery steam generator to generate the steam at night. So in this case, we studied how much fuel we burn at night, how much is the capital cost of the solar field, plus the cost of 30 megawatt or 40 or 50 or 60 or 100 to find the optimal size. Because also we use here in the solar field, we can use large field or a small field or medium. So we studied the parameter we studied was the size of the gas turbine, the size of the solar field, and we use parabolic trough or Fresnel in the water side, and we compare the capital cost. With Fresnel, we find, I think, the size of the gas turbine, the optimum is 50 megawatt. With Fresnel, I think this result is published in papers. You can see it in the papers I gave. Also, we tried Fresnel here. We tried solar tower to add the heat in the gas turbine side. Actually, there is something, how much this solar will contribute to the production of electricity and the steam if we use parabolic trough with the optimum size. As I said, we were changing the size, or we use the Fresnel, or we use the heat here. Actually, from our study, you find that if you add the heat in the solar energy in the water side, the solar energy contribution over the year will be about 8 to 10%. But if you add it in the gas turbine, because you add at the source, then the contribution might reach 30 to 33% from solar. So you have more chance, even without thermal storage. Even at night, you are using conventional power or use fuel. So these are just a quick idea. Now for us, I mean, the best when you have to add the solar to a conventional cycle to select a very efficient cycle, which is a combined cycle. The best is to have a more solar contribution. You need to add it in the gas side at high temperature, but this means more cost. The levelized cost with solar tower was higher than with Fresnel, but to use Fresnel, you have levelized cost is low, but again, you don't fully use the solar availability you have. So if you have large available solar sources like what we have here in the kingdom in our region, then it's better to add in the gas side. So that's why even the kingdom should work on developing the technology of solar tower. This is a good market, and if we invest on developing the technology of solar tower, bringing its cost low, as one of our paper we tried with a company in UK, as I said, we published this in a conference. The study showed that electricity cost from solar, in this case, if you integrate it with the Rankine cycle even, it would be cheap than PV. Now, for modeling, I mean power plant on software or computer, you need to determine the location of your place, longitude and latitude, gather the data from either weather stations you have or from satellites. We have website. You can contact CACAIR to get the weather data for the direct solar radiation and daily direct normal radiation, dry bulb with bulb and relative humidity. This also data that affect the performance. And get the average of daily and monthly, because you cannot use actually the hourly basis. Better because if you use hourly basis to get the average performance, it's better to get average solar radiation per the day or per month. For each month, we have one typical day, like in June, it is 21st of June. If you take the temperature, it is average of the whole months. For each month, there is a typical day. If you get the average solar data and that typical day, then it will represent the performance in the months. Take the average or take the instantaneous values. We have studied a very detailed study with Mr. Dabwan, and we have the result published in our paper in energy conversion and management and also in the CSS. If you need to get the performance factor of the power plant for cogeneration, you take the work plus heat produced over energy input. Energy input either from the conventional is M fuel time the lower heating value, or from the solar field, it is the efficiency of the solar field multiplied by the incident solar radiation multiplied by the area of the solar field. So we call it the aperture area. Actually, for modeling, as I said, we determine this. We have the some software like Thermoflow, Thermoflex. They have actually Thermoflex plus piece. You can build the power plant you want. It has all economics you have. Thermoflow package is a very expensive package, but it has all conventional power plant, gas turbine alone, steam turbine alone, combined cycles with inlet or cooling, without inlet air cooling. The gas turbine types, you have different brands like GE, Rolls-Royce, PP. For the steam turbine, also you have from different manufacturers. You have the cost of each component. If you have piece part of the software, you have actually a big database that is being updated always from Thermoflow company and the producer of these components of the turbines, the condenser, the pipes, the valves. Even it has the prices of the land. If you are building your plant in Saudi Arabia, you have the cost of the land. If you are building it in Egypt, you have the cost of the land. It's part of the capital cost. Also, type of fuel you have, depend, you are using natural gas, you are using what oil, what combination of oil and gas. So it has the fuel cost, it have the maintenance cost. All these costs, as we don't worry about it, it is built in. Also performance thermodynamic data and this thing is built in. You have another software that might not have economics, this Transys and Aspen Plus. I think there is one model also, software is available free, but it needs a larger space. I downloaded many times and removed it because of the space. It's called Solar Advisor Model or SAM. This is actually for management people. They decide they go for solar project or not, because it focuses in the economic plus, of course, thermodynamic performance, but not detailed thermodynamic performance as the first three. First one has thermodynamic plus economic. Second two, they have only thermodynamics, but they have more flexibility in the modeling. Thermoflow, you might have limited if you have like something called solar fuel reformer or fuel reformer, it doesn't have the model. You can add a component and write your model, but it is not as flexible as Aspen Plus. But the drawback of 2 and 3 is the economic part is not there. Solar Advisor is focusing more on the economics. There's some innovative ideas to use solar for cooling with triple effect. This cycle was patented by myself and Dr. Abdel Khaliq. We published a few years back. We have a solar tower that can give us heat to a sort of molten salt here, then have water in a Rankine cycle. The Rankine cycle or the turbine operate two compressor of a cascade cooling system. So we have very low temperature here, minus 50 for vaccination and storage. We have this ejector after the turbine to give us some cooling here for maybe air conditioning or some food storage. But we have here also the exhaust, while this relatively cold molten salt can heat absorption system for cooling for air conditioning. So we have here three refrigeration cycles driven mainly by solar. And we have absorption, air conditioning level of temperature. We have ejector for food preservation. We have freezing or cryogenic application here. One of our students was Dr. Antar, took course with Dr. Antar. He took this cycle and replaced here the turbine to produce power here for electricity, and also take the exit here to operate flash steam evaporation or flash evaporation desalination system, and also some electricity to operate RO system. This patent also was published. Another patent, I used the solar to add energy in the gas turbine side, but we divided the hot air into two parts. Part to go to the combustion chamber to reduce the fuel consumption, to produce the heat we want in the gas turbine, and the exhaust to go to steam or heat recovery steam generation to produce steam for either a process, or we take, also we help it by solar here, and we take this steam for what we call part of steam for fuel reforming. Fuel reforming actually is an endothermic process in which you take fuel of low heating value like methane, CH4, you mix it with steam or carbon dioxide, you need to add some energy to have some reaction to convert this methane into CO plus hydrogen. Carbon monoxide is the fuel actually, but hydrogen is the more valuable fuel. So sometimes you need to separate the hydrogen for fuel cells, so for example, or you have the same gas all over, but it will have higher heating value. If you have a fuel with lower heating value and you react it with steam or with CO2, CO2 is a good recycling, and you produce fuel with higher heating value, this means that you store the energy you added. If this energy is solar energy, then you are storing solar energy in form of chemical energy. So if you have a syngas with the higher heating value, you can compress it and it will take limited space compared to thermal storages. Now, this is chemical storage. You can compress the gas at high pressure or even liquefied. Then use this fuel to burn it at night. So you are actually using the difference of energy content in the lower heating value fuel into a fuel with heating value that is higher than that. So this sort of chemical storage. We have also another patent by myself and one of my PhD students that we produce hydrogen, and we have actually zero emission from this power plant. So we have a solar field that can heat the air, and we take the air and separate it through ITM or oxygen transport membrane to convert to absorb oxygen alone and to have nitrogen. We can take nitrogen that is depleted from oxygen but still at high pressure. We can run this nitrogen to expand in a turbine. The turbine can run the compressors that we needed to compress the air into this ITM. Then we take the oxygen to burn some fuel with oxygen only. So if we have oxygen and CH4, then we produce CO2 plus H2O. H2O, I can condensate it and take CO2 alone for sequestration. But also I can take this CO2 for added for methane in the fuel reforming and convert it to a fuel with higher heating value, or CO plus hydrogen. Then I can, with a palladium membrane, I can separate the hydrogen alone and take hydrogen, which is very clean fuel, and the remaining CO, I can burn it to convert it to CO2, and I take the CO2 again to recycle CO2 internally in this. And in this case, when I burn oxygen with the fuel or with CO, I burn it, then I get CO2, and CO2 I use it for reforming, and the H2O I condense it, so I can produce hydrogen and water, and I can produce power at the end. So this is actually triple generation. This is another cycle with the also combined cycle, adding solar into the gas side and generate steam for power with the helping here. But actually we take the steam here also part. Instead of condenser, we use it in multi-flash evaporation system for water desalination. And also this carbon capture process need for the chemical looping to need solar energy to actually the CO2 and nitrogen, you pass through a liquid that is chemical liquid that absorbs the CO2 and leave nitrogen. So you can here take the CO2, separate it for sequestration, but you need to heat it. To heat the liquid after absorbing the CO2, you need to heat the liquid. We heat it by solar. This is also patent, has been published. But I would like, if you are interested any time, to make a thermodynamic analysis for such a cycle or for any this we have already make a thermodynamic analysis. We have optimization using even genetic algorithm. We have 2 papers published from this journal, Applied Journal, Applied Energy with a very high impact factor. We have 2 papers and we have 1 patent, actually 2 patents in this and 2 papers published. This one, I didn't have a thermodynamic analysis for it. This one, we have the student with Dr. Hunter and myself has a paper we didn't publish yet, but it's a pattern that's published, paper is not. Here we have the same student did his master thesis with me and we published paper or 2 or more than this. These are quickly some innovative ideas to use CSP, either for power generation mainly and also for cooling. Now, if we look at the projects you have.
Doctor.
Yes.
This patent, is it applicable? I mean, can be manufactured and
actually, this patent, as you see, it's a system. It's not a component or a device that you can easily build. We have some patents actually for solar cooling that is we can build with a company like Xamil. We have agreement with them to build something. But this one is large scale one. It need to be adopted by a larger company. We have some work with GE to look at the fuel reforming. We have work now with Aramco for the fuel reforming. They saw my papers for hydrogen production because Aramco now is interested to produce hydrogen because the world now is interested in hydrogen energy. So Aramco is thinking to have to convert heavy oil into hydrogen. And they have project actually with us on modeling and developing the membrane for hydrogen separation. I am part of the team working in hydrogen separation with Aramco based on the technology or the idea, not my patent, because already this is there, but the system itself is the patent. But the concept of hydrogen separation is not new. Concept of fuel reforming is not new, but to produce hydrogen, power, and water, the system itself is the patent, is a new idea to integrate things together in this way. But we are working in developing the membrane that make or help the hydrogen separation very efficient. So we are, Aramco is developing the material because actually they built something with, they have some project with the Colorado University, they have some project with the Korea Institute of Technology, KAIST, and they have a system in Aramco. And they came to us to develop the membrane. And maybe with time we come up with if they adapt our system or not, but we are on the research phase of developing the material, you know, and also making the CFD to see how much hydrogen can separate, how to improve, what are the required temperature, what are the required pressures. But usually in the patent, you introduce an idea, right, of doing things. But how you do it is another phase. So we go what we call proof of concept, and if the concept is approved or you find it workable, you go for another phase, how to develop the components, how to develop the technology, and this actually needs money. Okay, let us go to the project district heating, again is solar heating. Let me come back to these slides that I talked to you about it, about this, this system. When we talk about this system, actually, this is a gas turbine, and you have the output of heat recovery is to generate steam, right? This is for industrial process. But when we come to district heating, let me tell you what the story came from. few years back, I was giving like short course for a group of engineers about gas turbine performance and improvement from a Saudi electric company working in Tabuk. Actually, Tabuk city at that time was not connected to the grid. Now I think the grid is connected all places in the kingdom. But anyway, and as in each city, there is a power plant that mainly produce electricity to this city. So as you know, in the most of the kingdom places, the heavy or the peak load is in summer due to air conditioning. You know, all houses are running the air conditioning, so the peak load in summer, and usually in the noon time around between 12 and 5 p.m. and maybe at night also because of the malls and other things. So the peak load in summer, but in Tabuk and in the north area, the peak load is in winter. The peak load is in winter. And usually when the Tabuk was not connected to the network, there was the plant was tripping off because of the heavy load on the plant. What does the heavy load come from? Because each house, they have these heaters, electric heaters to heat the houses. And also they have other problem in houses because, you know, the heater usually you need to put it on the ground so the hot air go up by natural circulation. So there are some accidents. If you have some kids, they fall down on the electric heater, they get injured. And also they tube and other thing. Also, if you have moquette or carpets, there are its own problem. But I mean, from a city point of view, the plant is tripping off. So if you are using actually heating by a different technique, like for example, in my air conditioning course, I asked the student to study heating the house using a reverse air conditioning cycle rather than using electric heater. The COP actually, if using air conditioning reverse heat pump, you use it for cooling in summer and you reverse it to heat in winter. Then if you need to heat by 4 kilowatt in your house, if you use electric heater, you need electric heater of 4 or 4.1 kilowatt. But if you use the reverse heat pump, you will use 1 kilowatt if the COP is 4. So this, you are reducing the electricity need by 75%. This is the question I give it to my students as a practice. But in one study, I asked them to generalize this on Tabuk city. But in idea, I also give it to one group of my senior project to study this. If we have this gas turbine in Tabuk that produce electricity for the city of Tabuk, and we use the exhaust, and instead of throwing it directly to the chimney, why not to use it to heat water and build a pipe network to conduct this hot water to the houses. And we have a water heater in the houses. So we use hot water for dishwasher, for machines, for washing machine, for showers, using the hot water coming from the central plant. So this plant in this case produced hot water, or maybe also steam. I pump it in the, but hot water is better for pump work. And if we have hot water coming to my house at 80, 60, 70 degree, then I need in my house water hot at 60, 50 degree. I can mix it with the normal water to take a shower, or I take it to the washing machine or so on. So this is one way for district heating. We can select a city like Tabuk, and we can actually from the report of national census or تقرير إعداد السكان تعداد اللي كان في 2010 وممكن تشوف update for it. I have the report. I can share it with you on the blackboard that give you in Tabuk how many houses, how many apartments, what the number of people average in each house. You have a lot of data. Also, what is the power consumption and this and that. So you can get some statistical data and see a typical house, for example, 6 person, how much hot water they need per day. So they can, we can count all the city houses, how much the hot water needed per day. So we can avail it from the central heating system or heating water system in Tabuk Central Power Plant to produce hot water and distribute it, then what is the cost of the pipeline? What is the cost of pumping power? And see the cost of hot water coming to each house. We can compare this if we have each house install a flat water collector, solar flat tube or solar collector like Dr. Antar explained to you. If we give each house or each house start building or buying this solar heater, that will work also during the day only and during night. There are some hot water now heater or solar water heater that they have the solar collector that and some storage tank, but also they have some electric heaters that can help heating at night. So you can see the cost, capital cost and running cost for both, either the individual solar heater for houses. If you assume, take the average house in a city like Tabuk, if you have, for example, 1,000 family, then 1,000 house, take the average one and say each house will buy this solar collector with this is the cost and running cost at night, what is this is electricity, then this is will be the cost. But if the city built the central heating system and distribute the pipe network, this cost will be divided on houses. And this is sort of just data collection and prices of the solar heaters, and also some strategic thinking to compare between two different technology, especially if you have in the gas turbine already working every day and the exhaust is going to the chimney with all pollution without really get benefit of it. So actually from fuel point of view, when you install the cogeneration for producing hot water, you add nothing for the consumption, fuel consumption, you add nothing. You didn't add anything to the pollution, you didn't add, but you save the electricity consumption that is load on the plant. Right, you save the electricity, and if you reduce the load in the plant, you're reducing the fuel actually, but you added the pumping power. So this is sort of analysis or a strategic thinking situation. Okay. The other point was the thermoeconomic analysis of gas turbine inlet air. You remember in module 4, we said that when you have the air is at low temperature, it has more density. Any compressor, when it rotates, it sucks a specific flow rate of fuel, because the flow rate depends on the volume inside the, between the rotor and the stator on the compressor times the rotational speed. So this volume is fixed and rotational speed is fixed. So the volume flow rate is fixed, then the mass flow rate will depend on the inlet air temperature. If it is low temperature in the air in a winter season or in a cold place, then you have high mass flow rate. If you have high mass flow rate, you can burn more fuel, because for have complete combustion, you have a specific air to fuel ratio. You should keep it for the good combustion in the gas turbine. So there is always a sensor. If the temperature is high at the inlet of the air, this sensor feels the temperature, quickly calculate how much is the mass flow rate of the air, so it reduce or increase the mass flow rate of the fuel. So if you burn less fuel in the combustion chamber, you produce less power, as simple as that. This is if you have a gas turbine like in Goraya power plant in the combined cycle, it is 180 megawatt in winter days. In summer days, it produces only 120. So you are losing 60 megawatt. Imagine 60 megawatt time 18 gas turbine or 20. So how much? 60 time, let us say 20. So it will be how much? 60 times 20, it will be 120,000 megawatt or 120 gigawatt. You are losing it in summer, where you need it in summer, because the peak load in the kingdom usually in summer, as I said. So what happened? If you try to increase this power to restore it back to 180 for each gas turbine, you need to install a cooling system for the air. So you have different options, different technologies. You can read about it. This is sort of literature or survey, from market survey or literature survey. What are the available technology to cool the air? What is the cost of it? How much it will save energy or restore energy? We can cool it by evaporative cooling, but this will make the air humid, and this will increase the work in the compressor. Also, it might lead to corrosion. We can spray water. We can also cool the air indirectly by air conditioning system, but this air conditioning system, from where it gets its electricity, we can get its electricity from the electricity produced by the turbine, but this will reduce the net electricity, but still this will improve the total. Or we can make absorption refrigeration using the exhaust gas from the gas turbine. But this means that we take, because the Goraya power plant is a combined cycle, we can take part of this gas for the absorption, reducing the power from the steam part, or we can use absorption system with the solar heating instead of heating from the gas, the exhaust of the gas turbine. So this project is mainly comparing different technology, the cost of it. I have a complete paper. I put it in the Blackboard, a complete paper on that with all details, with all economic analysis, but you need to read more literature on the same topic, write your report and decide which technology you prefer and justify why. I don't know how much calculation you will put, but this is again need whatever you decide or you need to justify. The other work, we can continue, Shabab, or you get bored?
You can continue.
I think we have three more ideas, and I will stop. Now we have the third project is comparative analysis of electric generation using CSP and PV and conventional power plant. As I said, we can have completely solar production from a steam cycle with thermal storage, or PV. PV also need storage, but here the storage is electric. You need batteries with PV, because PV will give you electricity only during the day. At night, there is no electricity from the PV. So usually people, they oversize the system to produce electricity more than needed. They use electricity they need for the daytime, but they save what they don't need in batteries. So at night they can discharge the battery, and they have, so also this battery storage, it depends how many hours you need to use it. Also like CSP, in the CSP, when you have a solar thermal, then you store thermal energy, like we discussed today in our lecture. So you need to compare the cost of PV panels plus the cost of batteries. This gives you the levelized energy cost of your system, plus also maintenance and other things. Compared to CSP, that you need to build the solar field integrated with the steam power plant, for example, and also thermal storage, and see the capital or levelized energy cost by adding to it the solar field, as we learned it in module 5. And then compare the levelized energy cost. In both, you need to compare with the conventional power plant that have only burning fuel. In this case, you might put the scenario that you have carbon taxes or so, but mainly speaking, we need to compare CSP with PV for power production for, let us say, 90 megawatt, 50 megawatt, whatever. I have a paper, the paper that we published in the conference. It is actually comparing solar tower with this, but now I have a paper submitted for a journal for parabolic trough rather than solar tower with thermal storage. We decided thermal storage to be 9 hours or 15 hours. This also increases the cost. So this is one of the issues. But in the conventional plant, please try to add the scenario of carbon taxes, because the main difference here between these three systems, that the CSP and PV, you might not have any CO2 emission, but in the conventional, you have the CO2 emission. So of course, conventional will be the cheapest unless we added carbon capture taxes or carbon taxes, or we add the other scenario of we put carbon capture. So how you make your project or your report more comprehensive and to cover all possible points, this help you to impose your thought and make an impact actually, because these technologies are available. But if you are the mayor of a city or governor of a city, so or general director or CEO in a company to build a power generation system, which technology will go for it? Also, the other one is,
Doctor?
yes.
Yeah, I'm part of Project 3. I just want to ask about...
Can we make the private question through WhatsApp or individual mails? Because this is general talk, and we are 4 now at 4.
Okay.
So because this is your project, of course, you are welcome for asking, but we need not to affect the class time. Of course, I have all, inshallah, all answers to you, but you can ask the question quickly just to learn about it. What is?
No, it's okay, Doctor. Later on, I will
okay.
call.
Now, the zero emission power plant, we were approached actually by a team from petroleum department. They are working with Aramco. They are trying to build a zero emission power plant in, I think, oil field, where they produce methane. And methane is very cheap actually to pump it from a very remote place to where you consume it, or to petrochemical industry. The transportation cost is very high compared to the energy value. So they thought, why not to build a power plant there to burn this methane and then transport electricity. Transporting electricity is very cheaper compared to pipeline, because you need just the capital cost to build the power, the cables. And then operation-wise, it doesn't have a really running cost, right? And also it will be efficient. You don't have pumping power, actually electricity, you produce it. And now the CO2 you produce, you need to sequestrate it, to store it in the wells. So it raises the pressure of the oil wells, or where you produce the methane, so you can improve or keep the production at normal rates, right? So you have here produce electricity, but you need to sequestrate the CO2. Regardless what is the use after sequestration, either we just sequestrate it to store it or to improve the oil enhancing. This is not the issue here we are targeting, but what is the design of the plant? So what are the technologies for CO2 capturing and CO2 sequestration? Of course, for sequestration, you need to separate CO2 first, because if you are burning with air, you will have 80% of the product is nitrogen. Nitrogen, you don't need to pump power to keep it under the ground. Nitrogen is not harmful. So better to separate CO2. So this will cost you some money, but the pumping power, you save a lot, because you don't pump all the exhaust product, that 80% of it or more is nitrogen. So you only store what, or you pay money for what you want to get rid of. So the cost of carbon capture or separating CO2 from the exhaust, this is, you can do it before pre-combustion, like using oxygen separation from the air, and you burn with oxygen, methane, or whatever hydrocarbon, CXHY, with oxygen produce CO2 plus H2O, no nitrogen now, because you separate it from the beginning by oxygen separation unit, and then you burn with oxygen, then you have the CO2. You can take part of it, circulate it back with oxygen to reduce the temperature, so the CO2 will be the inert gas instead of nitrogen, and the CO2, the most of the remaining, you need to compress it, and this is caused to compress for high pressure to inject it in the store under the ground. Or you don't separate the oxygen at the beginning. You have the air, you take it, burn with air, then you have nitrogen plus oxygen plus H2O. H2O you can condensate, but nitrogen, or you need the chemical looping. Chemical looping, and to have the exhaust pass through a liquid that absorbs CO2 only, and then nitrogen will be free. You can exhaust to the air, and the CO2 that is a solution with CO2 rich, now you heat it, then CO2 will be separated. Now the cost is in the heating and in the chemical fluid, and then you take this CO2 compressor. It is the same compression like the pre-combustion. This type of technology, how to separate the air by air separation unit, which is refrigeration, you cool and compress until you liquefy the air, then separate it. Like any factories that produce oxygen and nitrogen bottles, this technology is very available. And also you can use ITM, the new technology, to separate the oxygen by ionic transport membranes. So you can compare these type of technologies, two types, and with the pre-combustion to produce oxygen, but also you can compare it with a chemical looping, which is post-combustion. So again, this will depend on literature survey, market survey, and you need to write a complete or well-based opposed project. Or you have a solar integrated power plant like the ones I shared with you. You integrate a solar with only steam or only gas turbine or with combined cycle. What are the options you have? Which one you integrate better? Based on some literature and analysis of the literature, I think. And also when you decide which technology is better, you need to analyze it more and give us a clear performance analysis for it. Of course, in the lecture, third lecture I put today, I put the performance metrics if you are integrating with combined cycle, but also you can look at cogeneration, whatever the literature is full. I give you key papers that I have contributed in with my students or my colleagues. These are just examples, but literature is full. You will find each one of our papers, you will find maybe we have 40 to 50 papers as references. Also, I put a review paper with a revision on solar or CSP in general. These have more than 120 papers as references. So by this, I want to stop because the other two projects, I think Dr. Hunter have the key ideas on them. Maybe next class, he will join us after the exam to talk about it.
Maybe I can just save time by sending the detailed information of both to the groups. Maybe that, because I just formulated in a way that they have all the information needed.
But I think Dr. Hunter, for the 5 topics I give you some details. You can share
yes,
this
exactly.
write-up with them.
I'm going to, I will share it right now on the Blackboard so that they are all available.
Right, okay, clear. And also, maybe you and I sit together to see what is the milestones or the main contents they have to work on it.
Yes, yes, you are right. And then we can just put it in a separate folder or separate file that would apply to all projects.
Okay, yeah, yes. Please. But at least now give them some details. I think I tried to give some ideas. I don't know, I was going fast. But
I think, I mean, each group is going to approach you for these 5
yeah,
items.
for the items, they are welcome. They are welcome. But also maybe you and I sit together to give a general outline to balance the load in each group.
Yes, that's right. Inshallah.
Thank you. Thanks.
6 with the enter.
What?
Project number 6 is with enter. Dr. Enter.
Number 6 and 7.
6 and 7, yes.
Actually, the project is all with us both, but we were sharing thoughts. I mean, of course, any topic you can ask me, you can ask Dr. Antar, I think, but just because I have worked in the first 5 previously, and Dr. Antar worked in these 2 previously. So, of course, you are welcome to ask in the WhatsApp group, so the question go to everybody. If I have the answer, I will. If Dr. Antar have the answer, he will answer. What do you think, Dr. Antar?
That's fine, Doctor. That's okay.
Right. But of course, mainly Dr. Antar will be responsible about 6 and 7. But I mean, in handling, putting the plans, Dr. Antar and myself will put together.
That's okay. Actually, we have next week also exam with you, Dr. Enter.
Yes, that's right, inshallah. Yes.
And homework, and also we need the help session with you, Dr. Enter, regarding
Yes, we can arrange the help session as it used to be. Like, for example, we can make it on Tuesday at 8 p.m. I'll just upload like an announcement in Blackboard so that you would know about it and put the link as well.
on Tuesday.
On Tuesday, yes, inshallah.
It will be through Zoom, yeah, Dr. Hunter, or
Yes, Zoom, inshallah.
So please send it to me as well, so I can join.
Fine.
Because,
all right.
I didn't know what exactly you cover in this solar, and I was talking
yes.
about previous courses, but I actually didn't cross my mind that you already covered last week.
Oh. Yeah, actually, I did cover the introduction, which is talking about I mean this issue of the angles. We did enough time last time to talk about the flat plate and the evacuated tube collector, so that's what we'll be keeping for the last week, inshallah.
Okay, I think I should focus now on the wind energy for the.
Yes, for the remainder of next week's class, inshallah. Yes.
May I take little part to just to cover the concept? Actually, I found in the book actually 2 problems on CSP. That is not focus on the CSP actually, other than that levelized energy course, which is we already handled. But I want to quickly go through these 2 problems.
That's
because
okay.
There is no more homeworks, right?
Yes, I guess so. I mean,
so just for the benefit
of this week, there is a homework, which is homework number 3. And after that, there will be, I mean, they'll be working on the project. And
so I solved the problem with them at the beginning.
Okay, fine.
I mean, I put the problem in the 3rd session, but we need to just quickly discuss the solution.
All right. Okay.
دكتور عنتر.
Yes, تفضل.
بالنسبة للاختبار هل المجالات راح يكون على النيوكلير ولا كيف الديستريبيوشن راح يكون؟
We are going to have 1 problem related to the nuclear and 2 problems related to the solar part that we covered last week.
Okay, and nuclear, يعني we are aware of solving the homework questions only. Or,
it will be something close to what you have seen in the homework, basically.
Because any differences, honestly speaking, يعني I wouldn't be able to solve since we haven't had any opportunity to solve any questions during the class.
Yes, I understand.
So I don't know, like if a question is changed somehow, I'm not sure how we can solve something that we haven't taken.
You would be able, inshallah, when you see it. Don't worry about this.
Okay, يعطيك العافية.
شكرا يا شباب.
دكتور موديول 7 و 8 هو اللي حيكون معنا في الاختبار؟
Next week there will be Dr. Mukhaymar with us, and to come back at the end, which is the last module, inshallah.
So next week you will have the exam and myself, right?
Next week, yes, we'll start with the exam and then we'll continue the rest of the module.
So the week after it will be last one.
Exactly, which I guess it will be 12th of December, inshallah.
Yeah. Okay. Oh, yeah. Semester finished.
Yes, that's right.
Doctor, can you send the announcement for lecture and?
For what?
For the test.
Okay. Thank you, inshallah.
Okay, thank you.
شكرا دكتور اسماعيل. شكرا دكتور.
عفوا اهلا
وسهلا. شكرا يا شباب.
شكرا يا دكتور عنتر. بارك الله فيك.
دكتور اسماعيل الله يحفظك يا دكتور. شكرا.
I will leave the meeting.
النهارده في حقيقة.
يا بارك الله فيك يا اخي. السلام عليكم.
عليكم السلام ورحمة الله وبركاته.